In this problem, let's say there's a container containing water and its vapor in thermal equilibrium, and you know the pressure is 150 kilopascal, and you know the mass of liquid water is 1 kilogram, and the mass of vapor is 3 kilograms. We want to figure out, first off, what the temperature is equal to, and we want to know what the internal energy is equal to in kilojoules per kilogram, and we want to know what the actual volume is equal to, so the actual volume in cubic meters. To answer these questions, we need to know something about the quality of the system, or the fraction of mass within the system that's in the vapor phase. So we can define quality is equal to the mass of the vapor divided by the total mass. We can call the total mass just m, and that's equal to the mass of the vapor plus the mass of the fluid. So you'd say the mass of the vapor divided by the total mass, and in this case we've got 3 kilograms divided by 4 kilograms, or quality of 75%. So the first question about the temperature is pretty easy to figure out. We've got vapor and liquid in equilibrium. The pressure is 150 kilopascal, so 1.5 atmospheres, and we'd expect that the equilibrium temperature ought to be greater than 100 degrees C, because it's under a pressure that's greater than atmospheric. So to answer that, we go to the saturated liquid table, and we look up pressure 150 kilopascal. We come up with a temperature of 111.35. The next question is, what is the specific internal energy of the system? And we use the little letter U for this, in kilojoules per kilogram. And to answer that question, we need to figure out the internal energy of the liquid phase and the internal energy of the vapor phase, and then use the relationship with quality to calculate the fraction of internal energy associated with the vapor and the liquid. So we could say the total specific internal energy is the fraction of the mass that's a vapor times the internal energy of the vapor itself, plus the fraction of the mass that's water, which is 1 minus x, times the internal energy of the liquid, the fluid. So if we look at the saturated water table, we've got the internal energy of the fluid and the vapor. We look down, temperature of 150 degrees C. Here's the internal energy, the specific internal energy of the fluid and of the vapor. And if I plug in numbers, what I come up with is an internal energy, a specific internal energy of the whole system of just over 2,000 kilojoules per kilogram. Another way to do this would be to use this third column, which is U. It represents the internal energy change between the liquid state and the vapor state, or going from the fluid to the gas. And each one of these numbers in this column represents the difference between this column and this column. So in this case, 2384.5 minus 29.302 is equal to 2355.2, and so on as we go down. So let's keep that in mind. So here are the two values for internal energy, the vapor and the liquid, and here's the internal energy change between the liquid and the vapor. So by definition, what we've got is U, the specific internal energy change between the fluid and the vapor, is equal to the specific internal energy of the vapor minus the specific internal energy of the fluid. And if I take this expression and rewrite it, and I plug in this expression for the internal energy of the vapor, I can solve for it. In expanding terms, what I come up with is this expression, and the internal energy of the fluid cancels out. And what I'm left with is this expression, where I've got the internal energy of the fluid plus the quality of it times the change in internal energy as the fluid goes to the vapor. So it's a little bit easier to work with, so I only have to enter the quality once into this expression, but I'll get the same number. So I plug in numbers for this, and indeed I come up with the same value, a little over 2,000 kilojoules per kilogram. So the last part is asking, what is the volume of the actual system? So the volume itself in cubic meters. And I can solve this a couple of different ways. The first way is to figure out the full volume is equal to the mass of the fluid times the specific volume of the fluid plus the mass of the vapor times its specific volume. So in essence what I'm doing is calculating the volume of the liquid and adding that to the volume of the vapor, and that'll give me the total volume of the system. When I look at the table, the specific volumes that I'm interested in are these two at the bottom at 150 degrees C. So here's the specific volume of the vapor and the specific volume of the liquid. So I've got 1 kilogram of the liquid or the fluid times its specific volume, 3 kilograms of the vapor, and I come up with a total volume of 3.48 cubic meters. The next way I could solve this, and I'll get an equivalent answer, is to figure out the average specific volume of the whole system. So I'm going to figure out the, I guess, V hat for this entire system, and that'll include contributions from the water and from the vapor. And once I have that, I can multiply that number by the total mass, which is 4 kilograms. So mathematically, the total volume is equal to the total mass of the system, fluid and vapor, times the specific volume, the average specific volume of the whole system. And just like before with internal energy, the average specific volume of the whole system is the quality times the specific volume of the vapor plus 1 minus the quality, or this would be the fraction of the mass that's a fluid, times the specific volume of the fluid. So when I plug numbers into this, I come up with an average specific volume of 0.87 cubic meters per kilogram. So if I take this specific volume and multiply by the total mass in the system, I'll come up with the total volume. And again, what I come up with is the same volume of 3.48 cubic meters. So here's some code in ease that I wrote. It's much more extensive than what you would need to do to solve this problem, but I want to demonstrate a few things. So I specified the pressure is equal to 150 kilopascal. I just called it P1. And I said the mass of the fluid and the mass of the vapor are 1 and 3 kilograms. And I said the total mass is simply the mass of the fluid plus the mass of the vapor. So a total of 4 kilograms here. And I said the quality is the mass of the vapor divided by the total mass, or a quality of 75%. And here I've got the temperature of T is equal to water evaluated at 150 kilopascal, P equals P1, and the quality of X at X1, so 75%. And here I've calculated the internal energy, the specific internal energy, in 2 different ways. And the first was just to use this int energy command with water. P is equal to P1 and X is equal to X1. So I could enter these either as variable form, or I could enter them directly and just say the pressure is 150 kilopascal and the quality is 75%. So I would expect UA and UB to be equivalent. And here I've calculated the actual volume of the system, or I'm sorry, I've calculated the specific volume of the fluid. And to evaluate this, I said water, P is equal to 150 kilopascal again. And for fluid, the quality is equal to 0. And for a vapor, the quality is equal to 1, or 100%. And here I've calculated the actual volume of the system in 2 different ways. And the first is to take the mass of the fluid times the specific volume of the fluid. So this would give me the total volume of the fluid, plus the mass of the vapor times its specific volume. Adding those 2 together, I ought to get the total volume of the system. And I can also do it by multiplying the total mass in the system times the average specific volume of the system itself, which I calculate using this command. So when I run it, I get a report of all my variables.